So, hello everyone, welcome back to my channel. Today we're going to talk over this problem of controls. So, Acme Aerospace is investigating the feasibility of building an electric solar wind sail, an e-sail for space exploration, and an engineer developed the following crude model for one segment of an e-sail. Here, the input to the system is Ft, and the outputs are Rt and theta t. The parameters are mk and ohm are constant. Construct an omega or construct a state space model for this system. Be sure to clearly define the vector of state variables, define the vector of inputs u, and write expressions for the A and B matrices. So first, we have to understand what a state space model is. So here we have that a state space model is a mathematical framework that describes the behavior of a dynamic system using a set of internal variables called states. It comprises a state equation, which shows how the state variables evolve over time based on the current state, inputs, and system dynamics, and an output equation, which relates the observable outputs of the system to the state variables and inputs. This representation, which uses matrices to define the system's internal relationships, is powerful for analyzing complex multi-input, multi-output systems, and is widely used in modern control theory and system identification. So key components. So we have state variables. Xt, which is a set of internal variables that fully describe the system's condition at any given time. We have the input ut, which is external signals or controls that affect the system, and the output yt, which is observable quantities that represent the system's response. We have state space matrices, and these are matrices that define the system's dynamics. A is the state transition matrix and describes how the state variables evolve on their own, relating the current state to the next state. B is the input matrix, which shows how the input affects the state variables. C is the output matrix, which determines how the state variables are transferred into observable outputs. D is the feed-forward matrix, which represents a direct relationship where the input influences the output without going through the state variables. So the equations. So for a continuous time linear system, the state space representation is x dot is equal to axt plus but. And the state equation, this is the state equation, and yt is equal to cxt plus dut. This is the output equation. So applications and benefits. Modern control. It is the preferred model for designing advanced control systems for complex multi-input, multi-output systems. System analysis. It allows for comprehensive analysis of a system's internal dynamics, stability, and overall behavior. System identification. It provides a flexible framework for estimating model parameters from observed data, including reducing model order. Simplicity and power. Despite its mathematical nature, the matrix-based notation simplifies the representation of complex systems, especially those with multiple inputs and outputs. So let's tackle this problem. We first have to define the state variables. So what are the state variables in our case? Well, we have x1. Let me see. So x1, yes, we have to define our state variables. So we can define it as x1 is equal to r, x2 is equal to r prime or r dot, and x3 is equal to theta, and x4 is equal to theta prime. And yes. So we know that the input system is ft and the outputs are rt and theta t. That's why we define it this way using the state variables. And then now we want to define the vector of inputs. But so for the output section, which is the state variables, um, we have r prime from here, r dot from here, theta dot from here, r from here, and omega. We actually don't have omega, but but we have it in this equation over here. So yes, and then now we want to define the vector of inputs. So the vector of inputs will be U1 is equal to F. Why is this so laggy? Like, so this one is the vector of inputs. Vector of inputs. So now we want to write the state equations. So what are the state equations going to be? Basically, we see that x1 dot is equal to x2 because r dot is equal to r dot. So x1 dot is equal to x2. And x2 dot x2 dot is equal to r dot, and we can solve for r dot by rearranging uh wait, hold on. No, x dot is equal to r double dot. And r double dot is equal to solving this equation for r double dot, which is going to be equal to negative k minus m times omega squared times r minus 2m omega theta dot over m. So then we simplify this equation by factoring out 1 over m. So we can factor out 1 over m and put negative 2 omega theta dot, which we can write as x4, minus k minus m omega squared times x1, since x1 is equal to r. Um, Now we want to find what x3 dot is. X3 dot is going to be equal to x4. And now we want to find what x4 dot is. X4 dot is going to be equal to theta double dot. And theta double dot is going to be found by solving the second equation over here for theta double dot. So we can do it is equal to ft minus 2m omega r dot divided by m. So it's equal to 1 over m times negative 2m omega x2 because r dot is x2 plus ft, which is actually plus u1. So we have gotten everything in terms of x1, x2, x3, x4, and u1. So now we can come up with our matrices, which is the matrices A and B. So for matrix A, remember what matrix A represents. Matrix A, and these matrices depend on the definition of the state variables and the input. But matrix A will be equal to the state transition matrix. So basically, we have the definitions here. So A is the system matrix and it describes how the states influence each other. B is the input matrix and describe how the inputs affect the states. So why do we use state space models? So we already know some reasons, so let's go back. So the matrix A is going to come from uh the equations for x1 dot um x2 dot x3 dot and x4 dot. So the matrix A is going to be, let me see, let's move this down a little bit. Matrix A is going to be equal to uh basically we we don't have any like we don't have anything for x1 because basically this first row corresponds to x1 dot, so nothing for x1 because x1 is over here, x2 is over here, x3 column is over here, x4 column is over here. So we have 0 and then we have 1 x2, we have 0 x3 and 0 x4 for x1 dot. What about for x2 dot, which is the second row? We have um we have basically um from this equation over here, we have 1 x1, which is going to be negative uh negative k minus m omega squared divided by m, and that will give us negative km negative k over m plus omega squared. And we have no x2, we have no x3, but we do have one x4 over here, which is by negative 2 omega over m. Wait, and let me see. Did I miss something? Oh, yes, sorry. Yes, I just realized that I missed the m over here. So we actually have an m term over here. So not just that, but negative 2 omega m divided by m. So simply omega negative 2 omega. So negative, okay, 2 omega. What about for x3 dot? We only have x4 in that row of the matrix, so we have 0, 0, 0, and 1. And what about for the x4 prime row? We have that x4 prime is equal to this equation over here, and this equation over here simplifies to only x2, so we don't have to worry about x1. x1 is equal to 0. So we have negative 2m omega times x2 over m, which is equal to negative 2 omega and 0 and then 0. So now it's time to find the matrix B, but let's clean this matrix up a little bit first. Yes, the matrix B is going to be the input matrix. And what is the input matrix going to look like? So B is going to be, what is the input? Yes. So U1 equals F is the vector of inputs. So basically, the B matrix represents how each input affects the rate of change of each state variable, and B has rows corresponding to the states. And here there are 4 states. And B has columns corresponding to inputs, and here there are only one input, which is f of t. So only the last column is going to be fulfilled. So the position of ft in the B matrix depends on which state your derivative it directly influences, and each row of B corresponds to a state derivative. So why is ft in the last row of B? It appears only in the equation theta double dot is equal to x4 dot, the fourth state derivative. And thus the fourth row corresponds to x4 dot, where ft shows up directly with a coefficient 1 over m. So as you see in our problem, basically the vector of inputs is only f, and the state variables, we have 4 state variables here. And so u1 is actually equal to f, so theta double dot is equal to 1 over m negative 2m omega x2 plus f, and thus we see that we only have one input term and it appears in the theta double dot, and the coefficient is 1 over m. So we put 1 over m in the matrix. So you have 0, 0, 0, and 1 over m for B. And why is it on the fourth one? Because we have, as we saw in the previous, we have 4 states, or n equals 4, but one input, which is m equals 1. So I hope this problem was helpful in helping you guys find the A and B matrix. And see you guys next time. I'll be posting these slides afterwards too.